All right, today we're going to tackle one of the absolute giants of physics, but from a completely new angle. I came across this source that argues a puzzle that stumped scientists for over a century might not actually be a puzzle at all. It might just be a simple geometric mistake. So let's dig in and see what that's all about.
So, what if one of the most famous experiments in all of physics was just based on a simple targeting error? I mean, seriously, the source material frames this whole big paradox not as some deep mystery of space-time, but as something as basic as a hunter missing a shot. It's a really bold claim, for sure, and it's pretty much the core of what we're going to unpack here.
Okay, so to really get what's going on with this new idea, we've got to rewind the clock. We're going back to the late 1800s and the famous Michelson-Morley experiment. See, back then, everybody in physics was pretty sure that light had to travel through something, you know? Kind of like how sound needs air to travel.
And they called this something the luminiferous ether. It was this invisible, space-filling stuff. Now, if the ether is real and the Earth is hurtling through space, then we should be moving through it, right? Creating this kind of aether wind. The whole point of the Michelson-Morley experiment, which was super clever, by the way, was to finally detect this wind and measure how it affected light speed. So they run this brilliant experiment. And what do they find? Absolutely nothing. Zilch. Nada. No matter which way they turned the machine, no matter the time of day or year, the speed of light was always the same. This null result was a massive shock. It completely broke what everyone thought they knew about physics and kicked off this huge crisis that, well, eventually led to Einstein and his theory of relativity.
Okay, but here's where this source we're looking at just takes a hard left turn. Instead of saying, okay, we need a whole new physics of space-time to fix this, it says, hang on, what if we just messed up the basic geometry? And to make his point, it uses this really cool, simple analogy about shooting a target.
So look at how this breaks down the problem. On one side, you've got a static shooter. They're just standing still. They can use every bit of the bullet speed to aim wherever they want. Easy enough. But on the other side, you've got a shooter on a moving train. Now things get tricky. A chunk of that bullet speed is automatically spent just keeping up with the train's motion. You can't pretend that motion isn't there. The bullet has to do two jobs at once, move forward with the train and travel out towards the target.
And right there, that's the whole ball game. The source is arguing that the original physicists basically treated the moving experiment, the shooter on the train, as if it were the simple static shooter. They just kind of forgot to account for the velocity the light beam already had because it was being fired on a moving planet. So how does this targeting error actually play out with light? Well, this is where the source introduces this really neat idea it calls the light speed budget. And what's kind of cool is that the author apparently worked this whole thing out by talking to an AI to sanity check the logic.
The whole foundation of this is super simple. The speed of light, c, isn't just some cosmic speed limit. Think of it more like a fixed budget. Every single photon gets exactly 1.0 c worth of speed to spend. That's it, not one bit more.
And this budget isn't just a number. It's a rule of geometry. It works just like Pythagoras' theorem, from high school math. The total speed, c, is always the hypotenuse, that long side of the right-angled triangle. And the speeds in the other directions, those are the two shorter sides. You can change how you divvy up the speed between those two sides, but the total, the hypotenuse, is always fixed at c.
Okay, so let's watch this budget in action. Let's say our experiment, our moving shooter, is zipping along at 10% the speed of light. Now, when it shoots a light beam sideways, that beam has to also move forward at that same 10% of light speed just to keep up. It has no choice. That's a non-negotiable part of the budget. So, how much speed is left to go sideways? Well, you just run the numbers with Pythagoras. It turns out you're left with about 0.995 c. The sideways speed has to be a little bit slower.
At boom. This is the supposed mistake in all its glory. The old way of thinking just assumed light could go at a full 1.0 c sideways while also getting a free ride forward at 0.1 c. But if you add those two speeds up geometrically, you get a total speed that's faster than light, a superluminal bullet. It breaks the budget. And this source argues that this impossible assumption is the real reason there was ever a paradox to begin with.
Now, this isn't just some abstract idea. The source actually built 3D models to show us exactly what this looks like. So let's check out these simulations.
All right, so what we're looking at here isn't just a 2D drawing. It's a full-on 3D model in space-time. That diagonal line, that's the experiment itself moving through time. And those colored lines, those are the actual paths the light beams have to take if they're going to leave the device and then catch back up to it later.
And if you look at it from the front or the side, you see this really clear V shape. This is so important. The light isn't just going straight up and down, no way.
To keep up with the machine as it moves, its path through spacetime has to be angled forward, creating that v. And the total length of that v path? It's exactly the distance light can travel at its fixed speed, c, in that time frame.
This last view here really cements it. The whole journey is happening in 3 dimensions. And the source's big argument is that when you see it this way, the light beams getting back at the same time is not some crazy mystery. You don't need to bend space or slow down time to explain it. It's just geometry. The kind of stuff you learn in high school, just applied to space-time.
So, what does all this mean? What's the big takeaway here? Really, it's about shifting how we look at the problem, from a confusing paradox to something that's, well, geometrically unavoidable.
Okay, let's just run through the key points one more time. First, that famous null result isn't a paradox at all. It's exactly what you'd expect if you do the geometry right. Second, light speed isn't added up, it's distributed from that fixed budget. And finally, the miss, or the error, wasn't in the experiment itself, but in the old math that gave light an impossible, unlimited speed, which basically created a puzzle that was never really there to begin with.
And that really leaves us with a pretty wild thought to chew on, doesn't it? If a cornerstone of modern physics could really just be a simple accounting error, a mistake in how we budgeted the speed of light, it really makes you wonder, what other big laws of the universe are we overcomplicating? What else is just a matter of accounting?